Okay, apparently we need a little extrinsic motivation. The intrinsic motivation is not with us this morning. So, help me out here. What's the first Lewis dot structure look like? Okay, hold on. I have an FE. Okay, so we actually don't have a specific. Guys, stop talking to each other right now. You don't have a valence shell for iron because it's in the transition metals, right? So we have to figure out how to draw it. Well, because it is simply iron, you just have electrons everywhere. And what is this indicating?
Sea of electrons.
Delocalized electrons, right? So it's metallic. It's a metallic bond or metallic situation. What's the solid state conductivity? Highly conductive. So yes, it's conductive because of its delocalized sea of electrons. What about in aqueous solution, or when water is added to it? How does that affect the conductivity? Say again? So is it more or less same? Same, right? It's not dissolving. It's not electrolyte. It's not going to get any more conductive. So it's got the same amount of conductivity because the bond itself doesn't change. All right, what's the next one? Liquid bromine. What does that look like? Lewis. What does it look like? Lewis dot. Okay. So octet everywhere. Okay. So that's a molecule. Is it a polar or a nonpolar molecule? Why is it nonpolar? Right. So there's zero electronegativity difference there. So it's a nonpolar molecule. Oops, nonpolar. Okay. In its standard state here, is it conductive with other bromines or non-conductive? Non-conductive, because there's no ion formation, nor is there any electron flow. So non-conductive. And then when it goes into water in its aqueous state, what happens? Non-conductive again. It's a covalent compound that is not polarized in water. It's got some London dispersion properties to it, but it's fairly non-conductive. That's about it. Okay, next we've got wax. Okay, what does wax look like? It kind of tells you the problem.
C's and H's and
Okay, so how about we draw it like a organic structure? Okay. Carbon, hydrogen, there's just everywhere, right? It's a long carbon chain with hydrogen everywhere. Remember the little structures like this from organic chemistry? Each of these vertices are carbons. Okay, Nick, conductive or non-conductive? Why? Right, because this is a very nonpolar substance, nonpolar covalent molecule. And then when you dissolve it in water, does it dissolve? Why is it not dissolving, Clayton?
So many bonds.
Yeah, there's another way we thought about it too. So tell me more, Lewis. You said it's nonpolar. Why is that not dissolving in water? So what's the rule? Polar and polar, like dissolves like nonpolar and nonpolar. Come on, thank you, Gianna. Okay, so nonpolar versus polar water. Polar water likes to dissolve things like itself, either ionic or other polar molecules, not a nonpolar structure like wax. Okay, another word for wax is paraffin. Who's ever heard of paraffin? Kind of like parafilm, wax, parafilm, paraffin, anything like that, candles, they're all wax. That's like a bunch of different stuff. Sorry, this is more like candle. I think no, like, but it's a lot of different stuff. It's not just wax for candles. Like this is wax. That's like paraffin that you put on like the top of the test tube. So laboratory film. Okay. Last two. Okay. HCl. What would you guys say for it's what kind of molecule is it? I mean, what kind of thing is it? It's an acid. Is it ionic, covalent, network covalent, metallic? It's actually more covalent than ionic, but it turns ionic. So we kind of have this mixture here, okay? This is actually a covalent molecule because it does have H bonded to Cl like that, and it's Lewis dot. Okay, that is how it bonds. But this bond here is incredibly what? Why is it weak? So there's a large electronegativity difference. Okay, using our words here. Okay, there's a large EN difference, and so that large EN difference creates this weak covalent bond, which is able to dissociate very, very, very readily. But this is simply because of that dipole moment is so strong. Yeah. Did you draw as H plus and Cl minus? Well, that's what, if we draw it as it is alone, it's like this. But once it starts to interact, does it say solution? Okay, so in an aqueous solution, it will start to dissolve. So what I'm going to do is I'm actually going to show it both ways, like this. Makes H plus and Cl minus. Like that. Okay, so tell me about the conductivity. Very conductive, right? So the terms that you should be using here is that it's a strong electrolyte because it's a strong acid. It 100% dissociates, so forth. Okay, there's a lot of terms you need to use for your support for that. Don't just say because it ionizes. And so it's very conductive. What about in a further diluted state? Still conductive. Has the conductivity changed? So maybe, right? So it depends on how dilute we're making it. The farther we spread out our electrolytes, because these are strong electrolytes, so the farther we spread them out, the less the conductivity will be at that one location that we're testing. We actually have conductivity meters for this, so you guys can actually test this. So I'm going to say no significant change, but possibly depending on the extent of dilution. Just because you're not changing the amount of HCl, you're adding more water. Righty, so that was our solution of HCl. And then now we have a sodium chloride salt, right? So what does this one look like in its Lewis-Dot model? Lewis-Dot. An A plus and, okay, so this one's like a true ionic one. Okay, in this solid state here, what is its conductivity? None. Why? The lattice structure is stagnant, has a localized charge. The charge is unable to move, therefore it's unable to conduct. So it has a non-conductive, and in this case it's a non-conductive state. Because localized charges. Okay, so we're using our big words. What happens when I put an aqueous state? Okay, so what are some terms you could use to support that? You're saying it's conductive because so they are a strong electrolyte. Okay, so this is a strong electrolyte creating 100% ions. It's a soluble ionic compound. You can go further, but basically the conductivity will be very high. What would be solid at standard state and be a weak electrolyte when you dissolve it in water? So this one was a solid non-conductor, but when you put it in water, it was a very, very good conductor because it was a strong electrolyte. What would give us a weak electrolyte when it dissolves in water? Potassium chloride.
Iron.
The potassium is always soluble. Gia, always soluble. Sugar, not necessarily, because it is not going to dissolve. Dissolving sugar is not ionizing sugar. So I would say it would be a non-electrolyte more than a weak electrolyte. So there's three terms: non-electrolyte, weak electrolyte, and strong electrolyte. Sugar would be a non-electrolyte. Give me something else.
Mercury.
No. That one's gonna be metallic. It's always conductive. Beryllium fluoride, maybe. So I'm thinking solubility rules, right? Think silver, something that you know has a very, very low KSP. Okay, something that, like, for example, would precipitate, but ionize just a little bit to actually cause some ions to form, which would be electrolytes. But it's weakly electrolytic because it's not making very many of them. Does that make sense? Anything that's generally a precipitate, we know has a small KSP, would create a small amount of ions, aka weak electrolyte. Maybe beryllium fluoride. A lot of fluorides are actually insoluble. Potassium is definitely, because all of one is always soluble. So any precipitates with a low KSP value, would be considered weak electrolytes. What's something else that's not a salt that would be considered a weak electrolyte when it went into water? It's like big time review here. Polymers probably won't dissolve very well. Depends, like the polymer is a huge category. Go back to what we know. What would be a weak electrolyte because it doesn't ionize very well? That's not a salt.
Weak acids,
Weak,
bases.
right, so our stuff that's weak, right? Weak acids, weak bases would be considered weak electrolytes when they dissolve too because it's only a small amount of ionization. Okay, so I'm prepping you for your what's in that bottle lab. And then what's in your bottle lab, basically, I'm going to give you 4 substances and you have to figure out what they are. And that's all I'll tell you. Okay, I give you a list of about 100 things it could be. Okay, and you have to figure out what they are based on properties. So you're going to have to run a lot of tests, be super creative, and you're thinking of how you're going to solve for this, how you're going to double check it, how you're going to triple check it, that it is what you say it is. Dun, dun, dun. I'll train you on it when I do the teacher-directed part Wednesday. You'll do the student-directed part on Friday. Okay? Cool. Look at your notes from Friday. We're going to quickly finish this up from geometry perspectives, finish our lab, and then come back because my juniors are going to go on. I'm trying to introduce hybridization to you so that tomorrow will be a little easier on you because you have ACT. Okay? So this is not new necessarily. We kind of talked about this on Thursday or Friday. So we actually already have this part. When we look at the molecule, we look at the atoms, how does the atom geometry look to you? So you can tell which is bent, trigonal, planar, C-solid, T-shaped, all this jazz, right? You can look at it and tell me the shape. So this one has a little guide on how many atoms are there, how many are unshared pairs. But really the only reason we're considering the unshared pairs is because they're pushing the bonded atoms to create that shape. So we're good with the molecular geometries. That's what your whole lab is on, okay? The molecular geometries considers the shape of the atoms. They look for the atomic arrangements. Whenever we're considering electron group geometries, the electron group or electron pair geometry is simply counting up everything, bonded electrons and non-bonded electrons. They come in 5 varieties. So these right here I think are easier because you're considering everything equally, not bonded versus non-bonded unequally. But for example, tetrahedral can come in 3 varieties. Give me 3 examples of a tetrahedron. Examples like Lewis-Dot or the formulas. So one would be like methane, okay? That one has 4 atoms attached to it. Something with 3 atoms attached to it, to the central. That still has a tetrahedral electron group geometry.
XCF4.
XCF4, that one's going to have 6 electron domains. Something else? Say again? That's ionic. Stick with covalent. Okay, ethane around each carbon. That one's got 4 electron domains. That's carbon with 3 hydrogens. Carbon with 4. With 3 hydrogens. You're still including the carbon attachment there. What's the simplest one that's trigonal pyramidal, people?
NH3. Nitrogen
NH3. Okay. Let's think simple first. This is a tetrahedral. It's got 4 attachments. We know that. This is considered tetrahedral in electron group geometry because how many electron domains are there? 4. A lone pair plus hydrogen, hydrogen, hydrogen. There are 4 electron domains. Tell me something that is bent but has 4 electron domains. Water. Okay? So these 3 are classified as tetrahedral in the electron group or electron domain geometry because you're simply counting everything equally, bonded and non-bonded pairs equally. Does that make sense? I had 3 people say it made sense. I have 18. Does it make sense? Okay, so look at some of the drawings that you have from your lab. Let's look at, what's one of them? What's one of your beginning ones? SO3? What does it look like in terms of a slip-stop model? So 24 electrons. Please don't be that person who does not count electrons. Okay, what's the shape of it? Trigonal planar, like this. 4, okay, it's equal. Formal charge is good here. So this one's actually simple. It only has how many electron domains. An electron domain is just a location where electrons exist. How many electron domains around the central atom? Right, an electron domain, there's one here, and one here. So 3 electron domains would be considered what electron geometry? What's the electron geometry for 3 electron domains? It's actually, in this case, the same as the molecular group geometry because there's no electron pairs. Just the shape. Trigonal planar, okay? So what you should see here is that if there are no lone pairs around the central atom, the molecular geometry is the same as the electron group geometry. Because, like I said, you only count the atomic structure in the molecular group. In this case, they actually are exactly the same. So electron group geometry is trigonal planar, and molecular geometry is trigonal planar. Give me something where it's different. So I know like water was one of our examples we just used, but I just want to double check here. We know water looks like this. What is its molecular group geometry? Bent, right? So molecular group geometry is bent because you're considering just how the atomic arrangement is with each other. And then what's the electron group geometry? Tetrahedral, because you consider everything equally. Are you okay with that? So let's go back to the 5. Tell me how many electron domains are in each of those structures. Oops. So how many electron domains are for a linear geometry? 2 most likely, right? It could be 1 with 1 attachment, or it could be like carbon dioxide. For example, carbon dioxide with around the carbon there are 2 electron domains. So in trigonal planar, how many electron domains? 3 tetrahedral, 4 trigonal bipyramidal, 5 octahedral, 6. So you can see it's just looking at the electron domains, not specifically the atoms. So that's one new thing. So if I specify electron domain geometry, you can only say these 5. There's nothing else. If I say molecular group geometry, you got all kinds of things to choose from, like seesaw and T-shape, for example. Okay? Shake your heads, people. Okay, yeah. Because it's when you look, it's whenever you look at the shape. There are 8 bases around it. 8 octahedron, there's 8 bases. Okay, so let's talk one more thing before we go to the lab. So this is my introduction to hybridization. Okay, I'm going to tell you the answers first, and I'll explain the theory later on a video. Is that cool? Okay, so answers first. Let's look at methane. All right, you might want to write down some of this with me. Methane. Tell me what carbon is bringing to the table in terms of its valence shell. So let's maybe do the electron configuration for carbon. Go. Electron configuration for carbon. 1s2, 2s2, 2p2. Right. I did that in my first organic test. I put 2p4 because I was like, oh, 4 valence electrons, and I got it wrong. I just wasn't watching. Okay, so how many valence electrons does carbon bring? 4. Its valence shell is here. Okay, so there are 4 valence electrons. How does that play into how this bonds? Carbon bonds to hydrogen 4 times, right? Okay, hydrogen only has 1 electron. Hydrogen is 1s1. So what type of electrons or what orbitals are coming together to make this model? So what I mean by orbitals are s, p, d, and f orbitals, right? Well, carbon actually has 2 types of orbitals it looks like it's bringing to the table to bond, s orbitals and p orbitals. Hydrogen looks like it only has an s orbital. What does an s orbital look like? Spherical, right? What does a p orbital look like? Well, it looks like a dumbbell, right? It's got 2 lobes, top and bottom. Well, the way that we're talking about atomic orbital theory here, okay? It's also called valence bond theory. But the atomic orbitals that come together to make this bond right here are hydrogen has an S-shaped orbital, which is a sphere. But carbon has two different orbitals, an s orbital and a p orbital. But what you'll realize is that, don't we draw each of these bonds equally? Yes? So there must be a mix of s and p orbitals, a blend, a hybrid, that forces them to become equal bonds four different directions. The way it looks, instead of looking like a sphere or like a dumbbell, is it looks like this. Okay? That's called a hybrid orbital, because it's a blend between an s orbital and a p orbital. Okay, and that little backside is supposed to represent the s part, and the side is supposed to represent the p part. So this is a hybrid, where this is an s and this is a p. So when I bring these together, I make a hybrid orbital. The reason I have to explain it this way is because, like I said, there's actually experimental evidence to show that these CH bonds are exactly the same top, bottom, left, and right. Okay, so what I'm showing you here is that this electron, these valence electrons here, which we've probably drawn before as like 2s, 2p, boom, boom, we actually have to show that there are four empty orbitals, or unpaired electrons in these orbitals, to allow space for these four hydrogens. So what do you think happens to this one? It jumps to p. I'm going to draw it for, upward facing, okay? So instead of being 2 and 2, it's actually like this. One empty there, one empty, or three, not empty, I'm sorry, unpaired. Unpaired, 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 unpaired. So where do you think the hydrogen electrons go in or get shared with? Right, this is where one hydrogen will go, one hydrogen, one hydrogen, one hydrogen. But if I allow that to happen, it looks like that bond here, this bond, this shared space, is different than these because I've got an s orbital and a p orbital. So instead of saying that they're two different shapes and two different sizes and orientations, we actually call them sp orbitals, or sp2, or sp3. Okay, so how many p orbitals am I representing in this picture? How many p orbitals? 3. How many s orbitals? 1. Okay, so when I blend these, I call them sp3 orbitals. Why? Why do I call them sp? Because there's 3 p orbitals and 1 s orbital. So what do you think would happen if I blended an s orbital and 2 p orbitals? What would that hybrid be called? sp2 hybridized. It depends on the atomic orbitals I bring together on what I call the hybrid. Okay? So I'm going to give you some more here, but basically, anytime you have 4 electron domains, how many orbitals are converging on carbon? 4 orbitals are converging on carbon, or there are 4 bonds on carbon. 4 electron domains will always be sp3 hybridized because all the numbers must match. 4 atomic orbitals, 4 electron domains come together to make 4 hybrids, 4 hybrid orbitals. Those 4 hybrid orbitals are called sp3 orbitals. But the way you can remember it is that the 4 comes into play when you add up the exponents. 1 plus 3 is 4. Okay, so then tell me what, I think we just drew one of these. Tell me what this one, tell me how many electron domains are here.
4. 3.
Yeah, so we're only looking at this at the central atom, okay? So there are 3 electron domains. How many atomic orbitals must come together to make those? 3 atomic orbitals. Okay, 3 AOs or 3 atomic orbitals. Those are all coming from sulfur. Well, sulfur ends at, let's see here, 3s2, 3p4, right? So that's like 3s2, 3p, 1, 2, 3, 4. How many of those are able to bond? Meaning they have space to share an electron. 2 of them, right? So that's what these are. This one's a double bond. This one is special. The VSEPR model we've been working with, valence electron pair repulsion theory, does not explain why the heck double interval bonds form. There's no background on that theory. So that's why we have another theory to expand our knowledge to explain this. And then we have another theory to explain why molecules form. That'll come in later. So let me finish up this word right here. 3 electron domains come together with 3 atomic orbitals. They make 3 hybrid orbitals. Guess what letters or what types of orbitals come together to make them? An S, okay, a P, and another P. Those are the 3 atomic orbitals, okay, SP and P. So what is that one going to be called? SP2. There are 3 SP2 orbitals on this model. And I won't draw them for you. Well, I mean, I could draw them for you. S. And then, I didn't draw it very evenly. But then there's an oxygen here, an oxygen here, and an oxygen here. And then there's a double bond. And you guys' heads are going to blow up here. There's a double bond that's not hybridized. That bond's like this to make a double bond. So I'm going to get into drawing those because they get kind of crazy. But what I want you to be able to identify right now is if you have 3, don't flip the table. There's more. I'll explain more. But basically, you have 3 electron domains. You bring together an S, a P, and a P. You make an sp2 hybridized orbital. What about if I have something like this? How many electron domains on carbon? 2 electron domains, okay? 2 electron domains bring together 2 atomic orbitals. What 2 atomic orbitals do you think in order are going to be coming together? So earlier I said SPPP, that made SP3. Second, we just said SP and P, that made SP2. What is this one going to be? S and P atomic orbitals are the ones that are coming together to make these areas as electron domains. So what is that one going to be called? SP hybridized. And so there are 2 SP hybridized orbitals, one on the left of carbon and one on the right of carbon, that's allowing for that overlap for that other oxygen to form. It's all based on the number of electron domains. If there are 4 electron domains, what is the hybridization? Okay, if there are 3 electron domains, SP2. If there are 2 electron domains, SP hybridized. There can be more, but those are the ones that are highly supported under this theory.
And so, for anything that's not SP, like.
No, it goes in order because do you remember the all-fall diagram? I'm sure you do. It's like 2S, 2P, 3S, 3P. You only, so this is the S, these are the P's. You only can hybridize things that are very, very similar energy because bonding is an energy-lowering process. And so what you can do is when you hybridize these, they come to something that's a middle ground. So instead of being S being low energy and P's being a slightly higher energy, you make 1, 2, 3, 4 SP3 orbitals or energy levels because that's an intermediate energy. And that's actually, I'm going to do a video with this because this has some theory behind it. Sometimes those, and I was just going to the answer, so you know how to answer these things before you understand the theory behind it. Okay?
So everything has a hybridized version?
Not everything. Right now, the only highly supported ones are S and P's. But like you can assume there's like a 3D coming up here. There are such things technically called sp3d orbitals, hybridized orbitals. How many orbitals are here? There are 5 orbitals. So how many electron domains are there? No. The numbers are the same. 5. So 5 hybrid. So you can see the 5 orbitals, like 1 plus 3 plus 1 is 5. There are 5 orbitals together, S, P, 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 and D. This you'll see that the only thing you have to do is label something what type of hybridization it is, and then draw them. I'm gonna work on the drawings later. So, okay, how about we finish our lab from Friday? Okay, and then let me come and check. We have about 45 minutes left. At the very end, I want to kind of recap this again. Okay. Peace. Go build. If you are done building, you have the repulsion units unless you did those already. There's the analysis questions on there. Have you done those? Okay, work on that. Who is not here? Kevin?
Me.
I think. Let me see if somebody scored at the beginning, and then you just kind of pick up where they are.
I think I have I'm gonna be a lab group for next. I'm going to lab groups. How about I go Oh, I'm gonna, yeah. It's called the molecular model.
13.